Whoops.
Hey,
How are you?
good. How about you?
I can't complain. I wish my students had done a little better on their first exam in college algebra, but that's that seems to be going around.
That's a tough class, and then it's a tough class during COVID, and yeah, that's a tough assignment for you.
Uh, but it's actually one of the courses that I want to teach eventually.
Yeah, perfect then. And you get to work on the case.
I sometimes feel like the higher level maths we start getting into, and in fact I noticed this in your lecture, not so much you in particular, just that we sometimes we get into this look how much smarter I am than you are kind of thing between different portions of math, and I'm like, and that really translates to everybody else that's like, I don't even why do we use the same word for two very different kinds of things? A good example is when you were talking about polytopes and polyhedrons. When I think of a polytope, I think of, it doesn't matter what dimension I'm in, it's that it has multiple sides. And then a polyhedron is closed, but that's not what it is, right? A polytope is bounded and a polyhedron's unbounded in whatever space. And I'm like, it's why do we have the same word for two very different things in different parts of mathematics? And that doesn't even get into some of the really like hardcore esoteric analysis proof kinds of stuff where I'm like, prove it that you have a sequence that does such and such. I'm like, okay. And so then the professor says, yeah, but what about this other sequence that violates a statement, right? No big deal. I'm like, yeah, okay, this sequence definitely I did not account for in my proof. My proof is wrong, no problem. Except that you can't give me this sequence except in your head. It doesn't exist. Why do I care? That's in some ways that's why I'm in Math Stats 1 instead of real analysis, is that I absolutely detest analysis. I'm like, there is value in rigor, but at some point we're doing rigor just for rigor's sake instead of doing the math. To me, instead of communicating my information clearly and concisely, I'm being rigorous just to be rigorous, and that it annoys me. So that's why I want to teach college algebra and pre-calculus, because then I don't have to worry about all that.
Okay, welcome everyone. I'm glad we've got a pretty big class. So this is just if you got any questions for the exam, and then I thought if you don't, we'll just work our way through the practice exam. I know you got plenty of other things homework assignments you're probably focused on. So unless there's any questions right off the bat, we'll just pull up the practice exam and slowly work our way through it.
I actually have a question, but it's about MATLAB, so I can ask it later if that would be better.
Is anybody else interested in hearing about MATLAB? Because we can we're not in a hurry today. So.
Sure.
Go for it, Kirsten. Go for the MATLAB question.
Okay, so I'm trying to do a function and then use the function in the command window. I'm not sure I'm putting the function in the right place, because when I try to use it in the command window, it doesn't recognize it and it gives me an error.
Okay, is this a function you've created or it's a built-in one from MATLAB?
I don't think it's built in, because I tried just typing in the calling the function without creating it, and it gave me an error message for that. So I don't think it's linear combination.
Oh,
it was in the tutorial too, so I was just trying to
okay, so that might be one that isn't a built-in one, and maybe it was referencing something else. So what were you trying to do? Hey, Maddox, what was your goal with that particular one? Or if you
trying to practice, yeah, so I was just trying to practice like writing a function and then using it.
Okay, maybe let's try something like this. Let me share my screen. Let me see if I can get MATLAB up. This will take a moment. So for the folks that just came in, welcome. We are going, again, this is sort of a leisurely class, any questions we have, and then we'll go through the practice exam. I thought we'll just pull that up and go through question by question. And then I'll talk about its differences from the exam on Monday. Right? So don't be alarmed when you saw like 10 calculation questions at the bottom. Like, I'm not going to ask you to do that many in an hour and 15 minutes. But for now, though, we're going to start. Kristen had a question about MATLAB, and she's wondering about making functions. This is a good question just down the road. So for this first exam, what you need to do for MATLAB is you need to definitely be able to take the take a model and pull out the A matrix, to run linprog. So you need to be able to pull off what is the A matrix, what is the A EQ matrix, what is the B vector, all that. So I'll ask you to create, like there will be a modeling problem for certain on the exam on Monday. I promise there will be a modeling, and that's the one that will take probably the most amount of time for most students. So like however you want to allot your time, if you want to tackle that one first, or if you want to do everything else and save that one for the end, think about your strategy. And once you've created the model, so there'll be plenty of steps, so plenty of places for partial credit on that modeling problem, so that let's say, for instance, you finish a model, then I ask you to classify it. But if you got the model wrong, I'm just going to look at what you did and how you classified your incorrect model. Did you correctly classify your model as LP and LPO? So they aren't linked. I guess my point is there's many steps in that modeling problem. They aren't linked. One of the steps is now enter this into MATLAB. I'm not making you enter in MATLAB during class time. That's kind of stressful. I'm just asking you set it up. What in MATLAB you need a linprog. What is the A matrix? What is the B vector? What's the AEQ? And sometimes those are empty, right? Those are empty brackets if you don't have any AEQ. Is there an upper bound, lower bound? What else? F, right? The objective function. So those are things you just need to be able to pull off of a modeling problem. And then Kristen's question, and maybe this is one we should save in the issue of time towards the end. She's asking about how to create functions in MATLAB, and you will need to do that, not for this exam, but after this, there's an assignment with your team. Once we get to chapter 5, we learn the simplex, and you will have to code the simplex in MATLAB with your team. So we'll learn how to do them by hand, plenty of those by hand, which helps you check your coding. And in that coding, then you may create a function. And so it's important to be able to create a function in MATLAB. And we'll do one maybe at the end today.
Yeah.
Whoever wants to stick around, we'll make a little like some function that's square or something really basic. Okay, so anybody else, any questions?
I just had on the email, it said Monday, September 22nd.
Did I do a
But
typo?
September 22nd is a Wednesday. So I was just making sure it's next Monday, right? And
It
not
is,
in 2
sorry.
days. Okay.
Please pass
cool.
that to all your teammates. Gosh, I hate when I do those date typos. That's terrible. It's Monday the 27th. That's the date we've said from the beginning. So please like text your teammates too. Thank you, Jenna.
For that matter, the actual test in Oaks is visible, but I mean, the title is visible and it doesn't open until Monday, the 27th. So
Good point. Yes, and so that will open at 4 o'clock, and those are few of you that will start early. You have accommodations, and I'll email you again separately, and we'll take care of that. But otherwise, at 4 o'clock, or right before 4, I'll send a Zoom just like we did today. You'll check on the Zoom link, and I just need you to have your videos on. So it's required for me to proctor y'all. So, but I trust you guys. This is a departmental thing. You have to video it, and then you have that hour and 15 minutes, download it, however you want to, if you want to go ahead and print it and write by hand, if you like to use a tablet and write on it, and then you'll, just like your homeworks and your quizzes, you'll upload your work, and this one will have partial credit. Unlike the quizzes, there's no multiple choices, and well, actually there's some, there are, we'll go through the practice exam and you'll see the idea. But the point is you'll get partial credit. Hi, May.
So it's not open notes or open book or anything. It's all
Right. Yeah, that's why we're proctoring it. But make a study guide, share them with your teammates. The key terms, key things you need to know.
And it's okay to use the tablet to write the test on?
Yep, absolutely. I actually meant to do that in last week's shout outs to talk about some of the different homework quiz homework solutions that are submitted. It's fun to see some people by hand, and let's see, Zach always texts his up. Chloe does a nice mix of like screenshots and handwritten, and yeah, so you're welcome to do whatever you've been doing for your homework works, as long as I can read it. Okay, so maybe let's start just with the structure, and again, pass this on to your teammates who aren't here. The exam, I can tell you some details about like the number of questions and the type, and then we'll start working our way through the practice exam together. Okay, so let me pull up. Okay, so if you've had class with me, and I know a few of you had, you know, my teaching style is I like to have what I call concept questions and some calculation questions. Now your textbook's great at the calculation questions. Those are great examples of the level of difficulty that you'll see. I try to reward diligent students. So like, you know, when I put those suggested problems, if you're someone who's worked every single one of them, there's a chance you might see one of those, you know, on the exam, just to reward people. But that's not necessarily true that they're directly from the textbook. I'll make up some of my own, I'll pull some from other textbooks. Okay, so then the concept part, again, we'll go, that's a little bit unfamiliar because you probably haven't seen that much in our book at all or in other classes. So we'll go over that with the practice exam. That'll give us practice on those concept questions. The concept questions are usually the first page or so of the test. So the first part is meant to be done rather quickly. You're not cranking away on calculations. It's do you know your vocabulary? That's the first place. Like if you don't know what these terms mean, you're gonna have a hard time with the concept questions, which sometimes are true or false, sometimes multiple choice, sometimes draw an example. Do you think the statement's true? I don't ask for proofs because again, this wasn't a prerequisite that you have proof writing, but I'll ask for justification for the concept questions. So this time I think there'll probably be, haven't quite finalized, I might change one or two, but it's probably gonna be 5 or 6 concept questions on the first page. Again, that shouldn't take too much time for you. And then there'll be a modeling problem, and that modeling problem again is where you'll probably spend most of your time. Here's a paragraph description of what we're trying to do. We want to optimize something subject to some constraints. So you have to formulate a model, classify your model, you know, answer some questions like, is the unimodal, is the feasible region convex? All right, so then you'll also be asked to do this particular one. You can solve it graphically. So make sure you can do that technique and find the optimal solution. So you're going to work your way completely through this one. It's a small enough problem, obviously, that we can do it by hand and graphical method. Another type of problem was, I believe this was chapter 2. In chapter 2, there was a good bit about how to set up constraints with indexed variables. Remember, you could have, like, we've done some that were xi, we've done some xij's, some xijk's. So making sure you can read a statement and translate that into, suppose it might say something like, there was some where they would even give you a hint almost like, if the decision variables are defined xijk, now write a constraint that represents such and such, and they give you a statement. So make sure you can do those. Classifying your constraints as linear, classifying them as discrete or binary or continuous. So just knowing your vocabulary for those. And then chapter 3 is improving search. So you have to know the improving search algorithm, how to get, you know, the direction of optimal improvement is the gradient, how do you compute a gradient? So there's a little calculus 3 there, and then move 1 or 2 steps, like do a few iterations of the gradient descent. And there's also, as usual, so there's only a few of you in the 451. You'll have questions for you that'll say next to it 451, this is optional bonus. So you're welcome to do those, but again, not required for those. The 551 students, you have to do everything on every question. In total, there's about 10 or 11 questions. Again, I'm still debating a few things. 10 or 11 questions. Time shouldn't be an issue because again, there's quite a bit that's concept. It's really that one modeling one that's going to take your time. So if it was me, I would probably do everything else and save that one for the end. Okay, so can I answer any questions about just logistics or structure of the exam right now? Yeah.
Okay, I do have a question. So the first exam only covers chapters 1 through 3.
Yes.
That's it. Thank you.
Perfect. Yeah, this is and the neat thing, Ashley, is this is the chapter 3 is really the foundation of, we'll see this idea of improving search over and over. We'll see it in chapter 5, we'll see it again in chapter 6. I don't know, do we do chapter 7? We'll see it multiple times this semester. So this chapter 3 sets the baseline, and make sure you do understand the concepts behind why improving search works. I think that'll really help set the tone for the class. But I'm excited once we get past this exam, because then we get to things that are very practical. Chapter 4 will be modeling all sorts of things, like much more complex, much more like real life problems. And then in the simplex method that solves them, which is just the greatest algorithm of the century, actually. I'm not the only one who thinks that. A lot of people think that. Okay, anything else? All right, let's go to the practice exam. So you guys can find this on Oaks, and I'll also pull it up, but I want to see your faces. So maybe rather than sharing the screen, let's all just pull it up on the side. You should be able to access this already in Oaks. It's under the exam part. And so there's 2 pieces. Again, as Kevin said, the exam, you can't access that until 4 o'clock, but the practice exam should be open. It's just a PDF file with 2 pages. And let's go actually jump to the second page first. So that shows some calculation problems. Again, I'm not going to ask you that many. I already told you what I have, but these would be good ones to practice. They're of the level of difficulty, of the flavor. Of course, any of your prior suggested homework, another great thing to go over. Okay, and then let's just start working through these one by one, and we'll pause and give you time to work on them, and then we'll talk about people's ideas for them. So let's take number 1. So give an example of an unbounded feasible region in R2 that is not convex. So I'm asking, do you know your vocabulary? Do you know what a feasible region is? Do you know what unbounded means? Do you know what convex and non-convex are? So go ahead and draw a couple pictures on your notebook or whatever, your tablet, however you work. All right, let's see if anybody wants to share. And you can either, like, if you wrote by hand, you want to put it up to the screen, or if you did it with tablet, and let's just see some ideas.
I don't know that I necessarily need to show mine. I just said that if my only constraint is, say, the unit circle and it has to be bigger than that, right? If my, so x1 squared plus x2 squared is greater than or equal to 1, right? So I have the unit circle there in the middle, but everything outside of it is the feasible region, then obviously the 2 points that make a diameter run a line through the infeasible region in the middle. So
Perfect. So Kevin's idea definitely hits the unbounded. It's the R2 feasible region. He even, and it wasn't required for this, but that's something you can do on the exam if you want to actually give an equation, like you said, x1 squared plus x2 squared greater than or equal to 1. And then he showed that it was not convex by picking 2 points and connecting the line through the circle. And that one reminded me of that D club problem. Remember that discount club where they have this? All right, anybody else?
I also just drew like part of a curve.
Oh, just a section of a curve. So let's think about that. Is that unbounded though?
No, that's not unbounded. Okay.
If you drew the curve that it was like a parabola that just kept on going, we could do that. Yeah, that would work. What else? Ashley's got one for us. I see lots of like sunshines. We need you to unmute again, Ashley.
Oh, basically what I was saying is they're pretty much the same as Kevin's, and those little rays coming, showing that it's unbounded. That's all.
Oh,
Just
gotcha.
different shapes.
Perfect. Thank you. How about this one? What if it was R2, the R2 plane, and it was quadrant, let's see how to take it, quadrant 1 and quadrant 3? Would that work? All of quadrant 1 and all of quadrant 3. So we're unbounded. Are we not convex?
yes, for example, if I pick, it wouldn't be bounded if it's the entirety of the 2 quadrants. So then say 0, 1 and -1, 0, that line segment goes through quadrant 2, which is not feasible.
Right, does that make sense? So he's saying it's this whole quadrant 1 and this whole quadrant 3, and they're unbounded. And then we just pick a point, and a point that's outside goes through. Yeah, so you do see those. In fact, you see that's actually a common type of non-convexity that has some structure and some special properties that we use a lot in integer programming. And there are techniques you can use, because really it's the sum of 2 convex regions, right? So that's a type of non-convexity that can be dealt with. There's ways to do it. It's still non-convex, but there's ways to, like, to get at it. So you might see, again, it comes up when we do the binary, like xij = 0 or 1 for something. And then sometimes you need to, again, keep everything in these 2 separate quadrants in higher dimensional space. So that's one that you will see. Some of these other ones, like the D club one Kevin drew and Ashley, again, you'll see those if you're actually drawing feasible regions in higher dimensional space too. All right, let's move on to the next one, unless there's any other questions. Cool. All right, no problem. So next one, draw a picture in R2 for which the following is true. So I'm already telling you, sometimes I ask you to do true or false, like the next one. This one I'm telling you, this is a true statement, but you got to draw a picture that shows me you understand this. If a linear program has 2 optimal solutions, then it must have infinitely many optimal solutions. So again, some things, go ahead and take a look at that, but some things I'm looking for, again, do you know your vocabulary? What's it mean to have infinitely many multiple optimal solutions? Where do optimal solutions occur for an LP? And then you're going to have to draw your contours in there that make this match. All right, looks like most people are done drawing. Anyone want to share? Okay, so what we needed was a feasible region in R2 for an LP, so it has to be convex. And maybe easy to just go with a bounded one, so just think of some polygon. And then if it has exactly 2 corner points, say it's right along this edge, not to be the optimal edge, I just need to make sure my contours are also linear and they move in that direction of increasing value. If it's a max, decreasing if it's a min. So, you could have labeled those contours as they march out of that polygon, get to the edge, and these 2 are the corner points. We're going to learn how to find those in chapter 5 using simplex. Those are optimal. If it has 2, then everything connecting on the edge between them has to also be optimal. Any questions on that one?
Can you draw an example of what you're talking about?
I don't have a tablet, so let me just say, here we go. Thank you, Ashley. Perfect. Okay, so here's her, put it back up there. Thanks, we'll talk through this. She's got the feasible region here. And then she put some contours, and this is the edge. So like this, I should trace right here. That's the feasible region. And then she put contours that are parallel to an edge, right? So these 2 are corner points that are optimal. If there are 2 optimal solutions, there must be infinitely many along the edge between them, because the only place they can happen on LPs are corner points. Remember when we did the by hand solution, we found that they always occurred at corner points. Optimal solutions have to occur at corner points of a linear program because of the complex feasible region. And then there were 2, those 2, of which then we have infinitely many on the line segment between them. Thank you, Ashley. Okay, let's move on to 3. The first one, maybe 3A, it's a true false. First, let's read it, and then let's see if we can remember which part of the book it's talking about. Before you guys try to think on this and think whether it's true or false, let's just see if we remember there was a key box in chapter 3. I just remember the number because I'm teaching this so many times, box 325, right? And it relates, what page is this? This is page 1, the bottom of 118 in your book. And it relates constraints to active constraints, in particular to the direction vector delta x. And so there's a box there. So take a look at that. And then after you've looked at that and studied that, because again, something you need to know how to form the delta x. And it's probably something you remember, but read it carefully because this is the type of true false that can trip people up. So think on it, and then we'll come back in a few minutes and see, we'll vote true and false. Okay, let's go ahead and vote true, false, and then I'll talk about the type of answers I accept, because there's lots of different ways to answer this. Okay, so how about raise your hand if you think it's true? All right, raise your hand if you think it's false. All right, why false? I think Ashley, I saw had an aha, so let's let you go first, Ashley.
I had to unmute myself because that square term on the 3x2. So when you take the gradient, it's not just going to be a 3.
Excellent. So I actually caught when I first looked at this just a moment ago. I tricked myself. I didn't try not to be tricky with questions, but I forgot that square. And I was like, oh yeah, because I remembered box 3.25. I don't have it memorized, but I know it's just the same linear coefficients, greater than or equal to 0 if it was greater than or equal to 0. So it's like pretty straightforward. And I was like, oh yeah, that's it, true. But then I went back and I did the exact same thing, Ashley. Like I had like an aha, and that's square. So we don't know. So one answer you could say is, again, if you're really diligent and studious, then we had this box, we learned this thing that relates to active constraints only. So there's only one, that's the only one we have to worry about, to the direction vector. And this box only applies to LPs, so linear constraints. And this is a nonlinear constraint. So we don't have a similar box. And in fact, I don't know that one exists, that there's something, because it's much harder to do nonlinear programming and have these nice, very clear relationship. So that would be acceptable. Another thing you might try is graphing. Like this is an R2, so you could graph that. This is similar to the example Kevin gave us, but it's not a circle. I guess it's some sort of parabola, square-ish looking thing, but outside of that region. And then maybe you try to think about the feasible direction. This is pointing us in a 2-3 direction. So you could try something on a technique that way. Any other ideas or approaches to this one? Okay, good. Let's go on to, and again, for these, so the next one, true, false 3B, you have to make sure for all of the true falses, you justify. So whatever your justification, sometimes it's just a tiny little picture works. Sometimes it's, or changing one word in the sentence. Because like that one, again, if you just say, I want to remove the square, and then it's true, and demonstrates that you know. Okay, so the next one, if improving search is applied to an unconstrained nonlinear minimization problem that has a concave objective function, then the algorithm is guaranteed to converge to the global min. So a lot of vocabulary in that one. Take a moment and think about it. Let's do a vote again. If you think it's true, raise your hand. If you think it's false, raise your hand. A lot of non-voters, abstentions. I'm up here. So I'm thinking on this one, maybe improve. So some of the keywords, unconstrained. Okay, so we just have minimize something and it's got an objective function. The objective function is nonlinear. So let's just take an example, maybe makes things easier. Try several examples. This is good strategy for this part of the test, is examples and counterexamples. You'll get better at this, even though again, we're not a proofwriting class. I think this gets us baby steps towards that. So one I might do is x1 squared plus x2 squared. What does that look like? Z equals x1 squared plus x2 squared is a circular paraboloid opening up from the origin. So you have something shaped like this. It's unconstrained, so all you have to do is worry about this function. We want to minimize it. Improving search, I could start here. I go in the direction of the gradient, negative gradient, because I want steepest descent, get to another place and keep on going. Will I get to a global min? And the key thing with my example was to make something concave. Oh, maybe I just did convex, right? I always get those mixed up. I was wanting the shape like this, right? Where I draw 2 points, connect them, and the function lies below it. So that does make it that every local min is a global min. Therefore, improving search has to work. I can't get stuck in a local min if it's a convex function, objective function.
I took concave to mean either it's either concave up or concave down.
That's exactly how it's used. And often they
and-
say
and-
convex too.
So a concave down function that's unconstrained doesn't have a minimum. So I can't, because it has a maximum.
Right, so I'd love to
So
see,
that would
this
be-
is another counterexample where depending on how you interpret it and how you drew it, I'll give you credit. So so this is a great example that Kevin's come up with. There's sometimes when I write a problem where it can be done true or false, depending on what you're thinking about the problem. That sometimes there aren't an absolute final answer. And I grade that way. I grade partial credit. Really what I'm trying to do is understand how you approach a problem and how you think mathematically. Okay, how about 3C? More vocabulary. A constraint is a redundant constraint, then we can safely remove it without affecting the optimal solution. Really, this is just asking, do you know what redundant constraint? And that's really a vocabulary question. A couple ways you could approach it. You could draw a picture. If you like thinking algebraically and with equations, you could write a small example. For the picture, we would take, say, Ashley's picture from before, and then have a constraint that's outside that feasible region or just barely touches, like sometimes they just go through a corner point. Those are redundant constraints. We didn't need them to define the feasible region. It was shrink wrapped without it and it was fine. Right? Maddox, did you have a question on that one?
I had a question, sorry. So when I was thinking of redundant constraints, that means like redundant across the board. Because I thought like with active constraints, like it depends on like the step you're taking. So it's like redundant, not exactly the opposite of active. Like is redundant like redundant from the start, or is it
Yes.
redundant at like that
Okay.
step itself?
Thank you, Jenna. That's a good question. So redundant is from the start. And in fact, maybe another way to think about this too is to talk about how industrial code at working for American Airlines, and I've got XIJK, LMs, like huge triple, quadruple indices, thousands of variables. It'll go in and try code, spends a lot of time trying to find any of these redundant constraints and remove them. And that's how people have done entire theses on how to find these. So it's from the start something that I can remove. When you were saying active and inactive is not the same as redundant. So active or inactive. Redundant is something that, again, isn't necessary to define the feasible region. It's excessive. It's handled by other constraints that subsume it, right? So like think about, again, Ashley's picture, that polygon, and maybe there's a dot for a corner point, and there's a constraint to find that just barely touches that dot, that corner point. But that corner point was defined by this other constraint and this other constraint, which are tighter to the feasible region. So this one was not necessary. If you removed it, the feasible region stays the same. If I remove some other constraint, a non-redundant constraint, the feasible region changes. And this was an example of one where a lot of times I'll talk about some things that aren't quite described as much in the book. So this is one where it was really straight from my language. I don't think Nargan uses that phrase much. Okay, 3D. True or false? It's possible for an optimization problem to have infinitely many solutions, two of which give a different objective value. Okay, so just take a moment and think about that. Often you have to read these a few times. All right, let's do our voting. It is election day in Canada. So. Okay, so think it's true? It's false? All right. So this one's a strange one because, I mean, maybe when I look at these, I often try to, if I was you, come back, this is optimization. Okay, well, she didn't say it was linear. She didn't say nonlinear. It could be either, could be integer. So you just start trying to think of classes of problems that might come up with counterexamples if you're thinking it's false. So it's possible to have infinitely many optimal solutions, two of which give a different objective value. And hopefully you just kept like, that's weird. Does that even make any sense? Can you have, would they both be optimal if one's like 11 and the other one's 12 and you're maximizing? You know, what does that 11 mean? It doesn't make sense. Right, so this one's false. It's really just a vocabulary one. Any questions for me on that one?
I came down on the side of false because, again, it doesn't make sense to have two different. If I'm looking for the best one, I can't. It doesn't make any sense to have two different objective values. But at the same time, if I think about that, that 3D whatever it was called, the where I have, right, I had this really high point at point 1, but at 3, right, with just optimal. Am I supposed to, is that supposed to mean globally optimal or locally optimal?
Great question. So again, here's one where Kevin, if you answer that, if you said true, let's say, and then added some language about, hey, I'm thinking global versus local, again, then I'd say, okay, that's a deep understanding of this. He gets it. I'll take his answer true. I was thinking of it that these are, when I said objective, when I said optimal value, I'm thinking about the global optimal. And you're saying, well, you weren't quite precise about your language, so I'm going to go ahead and tighten it up, and then I'd say true. And that's fine. All right, let's move on to number 4. Hopefully this one's pretty straightforward. If at any iteration of the improving search algorithm, the maximum step size that both maintains feasibility and improves the objective is infinity, then the problem is said to be fill in the blank. All right, what's the keyword here? Unbounded? Okay, good, unbounded. You can have an unbounded feasible region, but you can have an unbounded problem because the objective function takes one of those unbounded rays, right? That's really what they're saying. Maybe you're along the edge and the step size is infinity. I can just keep going in that direction forever. I'm following the ray and I'm going forever unbounded. Okay, number 5, draw a picture of a feasible region with a point that's active. Oh, so an R2 feasible region, that's key. With a point that's active at exactly 3 constraints. So I'm testing some vocabulary, of course, that you know what active is, you know, feasible region in R2. Okay, so we kind of talked about this when we were saying Ashley's picture, and then Jenna had a question about redundant constraints. So you could have, a point here, at my fingers, this is an active constraint, this is an active constraint, then we just need one more that comes in there any which way. And it turns out that then the feasible region, if it was this polygon under here, that this is a redundant constraint, right? I didn't need this one. I just needed these two. These are the tight ones, and this was a redundant one. That little cat tap on the shoulder was pretty cute. Just gently, come on, Mom. We're done, class.
I have a question.
Yes.
What if I had like three constraints? One was like y is greater than equal to 0 or x1 or whatever. One was y is less than equal to x, and one was y is greater than or equal to x. So then like the origin would be the point where they all intersect.
Oh, that's a great counterexample. Let's see. So Maddox is defined a half space and then a half space. And so it's just the line of intersection, and then that intersects with another half space. And yeah, we would just get the origin as the only point in the feasible region. So we have like what's called usually the trivial case. And so let's see, then does that point that is active? Yeah, that's great too. That worked.
Okay.
Which is another way, that's Maddox is a good point there. It's another way to think about these. Sometimes this is advice from my mentor at NC State. He often talked about when he was thinking about mathematical problems to think in extremes. And what he meant by that was like to think of the easiest possible case, and then the often it's the or the full case, well, hardest is maybe it, but like take it down. So what Maddox did is if the feasible region is just one point, then there you go. Like often that's the trivial case, the simplest case. If you can think of that, that's a great counterexample often. For example, in this case. Okay, number 6, this is another type of question you might see under the concept one. It's really just a big picture question. Do you know why you're doing when you're doing the phase 1 or big M? What's the point?
You mean the two-phase method?
Oh,
The big
yes.
M method?
Yeah, phase 1 of the 2-phase method and the big M. Yeah, thank you. What's the point of those?
To find a feasible starting point for the improving search algorithm in our original problem. If we don't have, if it's not easy to see where a feasible point to start, we can use this to kind of simplify, or in the case of the big M, it's not necessarily simpler, but in any case, it changes so that we can actually have some place to start.
Perfect. Yep, that's it. Just looking for a starting feasible solution. Okay, and then 7 is related to that. Suppose the phase 1 method to get an initial feasible value for an R3, X1, X2, X3 problem concludes with Y star. I probably should have had X star there, right? 1, 3, 1, 0, 0. What does that say about the original problem?
That 131 would be a good starting point.
So, and how do you know that?
Because the artificial variables are equal to 0.
Perfect. That's all we're checking. And how about if one of the artificials was non-zero, what can we conclude?
If it's global, then the problem is not feasible, and if it's not, then go back and
Perfect, May. So that's a little technicality we had when we learned the 2-phase method. Make sure if you know for certain, and when do you sometimes know if it has those nice properties, it's an LP. Okay, so any questions for me about this practice exam or the exam in general?
So like for the big modeling problem, so you'd basically ask us for the math lab component, like how would we enter those F, A, B, A, E, B, E, Q, like in, and we just write it out by hand.
Exactly. So I'm not going to make you open MATLAB and run a linprog. I'm just asking you like the command A equals linprog, or sorry, X equals linprog. You know, what are those matrices? I don't even ask you to memorize the order you put it in. I just need to know what's the F matrix for this. So you pull that off from the coefficients of the objective function. What's the A? What's the AEQ? Are there equalities in this? Make sure you separate those from the inequalities. Put those in. The inequality ones go with the A. The equalities go with the AEQ. What's the right hand side? Split that again according to the equalities and inequalities. Are there any lower bounds and upper bounds? So don't forget those. Those are ones students forget about. You forgot the simple constraints. Make sure you write those in your model. X greater than or equal to 0. And then when you're setting it up for MATLAB, make sure you form an LB equals zeros vector.
Yeah, I think there was like a worked out example and a couple practice ones in one of the tutorials.
Yes, that's exactly what you have to do. So go along with what I did there. And for that modeling one, again, my advice is probably if I was taking it, I would do everything else, save the modeling problem. And it just reminds me of grad school when I was taking some OR optimization classes. We had one class that was just a modeling class, so like what you're going to do in chapter 4. It was like all we did in that class, so we got better at modeling. But the test would consist of just like 3 problems, like 3 giant paragraphs, and that's all you had to do is model this. And you're just like so stressed, like if I don't, because some of them you need that light bulb turn on, right? You know, and so practicing those calculation problems that are listed, going over your old suggested homework problems that are calculation or modeling based, that'll put you at ease, because the more you do them, the better you get at realizing, asking the right questions, like what would be the decision variables? Because again, that's the big step. What decision variables help you answer the question? Often work backwards and just say, like, if I'm presenting this to a client, what does the solution look like? Well, I'd have to be telling them, like, there was that example of how many floors they're going to make in this hotel. I need to tell them what the diameter is. Like, sometimes working backwards that way helps you come up with decision variables. And again, this one should be doable because it's one we can do by hand. So like the modeling shouldn't be too rough on this one. All right, well, that's all I had for y'all. So if you want to stick around, if you got questions, and I know Kristen we'll do a, try to make a function in MATLAB, do a screen share and do that. But otherwise, if you don't, you're always free to go whenever. I'm not keeping anyway. All right, so any questions for me before I go to this MATLAB example? Open MATLAB first. So it'll take me a moment. I'll get MATLAB up and running. At certain times in my career and my research, sometimes MATLAB is just always running, right? But not up now.
I actually did have one more question, like a logistical thing. I noticed there wasn't a exam Dropbox set up. Are we gonna be setting that up, or like email it to you or submit it?
No, I will. Thank you, Maddox. That's my homework. I finish this. I will. First thing I could do is post this to Oaks for your classmates who work here. So we'll have the recording, and then I'll make a Dropbox for exam number 1.
Okay, thank you.
Thank you. And please do share with your teammates who weren't here just any of the tips you had from today, or they obviously can access the recording. And just know that my email had a typo. We are having an exam on Monday, the 20th. I said verbally, but typed it wrong. MATLAB takes me a while. My computer's pretty old at this point. 11-year-old.
Is mine.
Hopefully you learn though, like the different packages that you can, if it is so slow, like maybe jettison some of the other MATLAB packages. Like at the beginning you're shopping, like, oh, I want statistics and I want image processing. You want to just go a little crazy because you can.
I just got the 3 you mentioned. I didn't get anything else for that reason.
I have to force quit it because it's not responding, so it'll take me a little longer. Sorry. Just keep doing. Okay, I think I've gotten that one, and I'll pull up some M files that I have. I think I have. Just share my whole desktop here. So here's MATLAB. You're seeing this. Screen share. All right, so I open MATLAB, and I'm in a folder with some research things that are kind of M files that I was doing research with. And let's pick one. Okay, yeah, it should be simple. Okay, so then what opens up in MATLAB is a editor window. So I've already created this M file, but we'll do one from scratch too. But this is just to show you a few that I've done. Super small one. You need the function command at the beginning. That's telling MATLAB this is a function. You'll save this in the editor window. I saved it as mutateflip.m, so I decided to call the function mutateflip.m. This is my input x, my output is y. In this case, what I'm doing back here, let me see. X is a vector, so like 1, 2, 0, 2, 1. Okay. All right, so I have this vector. Let's see what happens if I'm in the right folder first of all. If I try to run mutate flip on X, what it's going to do. Let's so it spits out, and I can label that as y equals. If I want to call that an output of vector y, I will display that there. So I input a vector. I just made up one on the spot. And this mutate flip is just something for my research. I do a lot with ranking vectors. These are vectors that represent something, and I wanted to do evolution optimization on it. So I just needed to create one that sort of had some random components of it. And so I did that by this short little M file. And it copied the input and stored it temporarily in Y. And then it's going to go ahead and change that. It used some built-in commands called length, got the length of the vector. The vector is a 5-dimensional vector. It did a random permutation of those 5 things. So just randomly permuted a 5-dimensional vector. I can start displaying some of this myself. So it picked a couple random positions to be the flip positions. So I'm suppressing the semicolon suppressed the output. So now I want to display it. So I remove those. I'll save it and we'll run the file again. So all I'm trying to do in this function is start with the input vector. So let me display that thing. Oh yeah, it displayed it. Display that one as well. So I'm just going to display every step. All right, so I started with the vector x, and it actually looked like this. I replicated it and called it y. 1, 2, 0, 3, 1. Or let's actually make it more appropriate to make it a ranking vector. X's, these are 5 teams in some division in NFL or something. And the first place team is actually the number 1 team is actually 5th place team. So these are orderings of the teams, right? All right, now I'll run the command. And so what it did, it copied that exact same initial input. It did a random permutation of those 5 things, which is a built-in command in MATLAB. So it just randomly permuted the numbers 1 through 5, the answers 1 through 5, and came up with the ranking. I then, the function asked it to just randomly pick a position. The first position I want to actually flip was 2 and 4. So I went into this one, I picked the 2nd and the 4th, and I flipped them, 1 and 4. Okay, let me show you one that I think might make a little more sense for our class. This one I was trying to find all optimal solutions for a linear ordering problem. I'm just storing some matrices here that I'm going to use to test, so I commented them out with the green. That's another helpful thing that'll help you when you're making your down the road after this exam, when you're doing the next assignment in MATLAB, we have the MATLAB code, the simplex algorithm. This little percentage sign is a comment, so you can block comment things. You can put comments at the end of lines. So I was going to take a matrix, and this is showing, you should look familiar, AEQs, because I'm eventually down here going to run linfrog. Or no, I was running BILP, int linfrog, right, different times, setting up LPs and ILPs. So I needed to form AEQ matrices. But because these things were going to be so big, these are some tiny ones for me to work, but I was going up to like 100 by 100 matrices. I couldn't enter in, type in 100 by 100 matrix, space, colon, space, right? And so I had to build the AEQ using language. And so I built it up. This is where in each row and column, there was a pattern to this. And I was able to enter the AEQ matrix. And this was all I just had to run the command LOP all off, and it would do everything that's in this code here. And then we now go to one smaller example, which came from one of your MATLAB tutorials. All right, so I just want to copy this one of your tutorials. It's going to take input, and it's going to spit out output. That is just the sign. Oops, it didn't display that. Let me just put this in a editor. So now I'm in my editor. I want to open it. Right. A new one. Like that. Function, output. Equals, we'll call this class example. Input. Files up. Maybe not too clear on that. All right, so I just wrote this function. I like to use y's and x's, but this one in that example had inputs and outputs. So you're going to take input, and then you're going to call that, copy that into something called x, and then you're going to apply the sign to that. And then you spit out the output. And I just decided to call that class example. It's an M file. It'll save it in the directory that you're in. You can move that wherever you want. I'll keep it where I'm in, because that's the directory I'm in. We save this, and then we go back to our work command window, and we can try running class example. It needs input, right? So we have to class example of x, and it spits it out. What was x? X was that ranking vector, but it doesn't matter. We can make x anything we want. It could have been a scalar, it could have been a vector, and it's just going to apply the sign function component-wise to that, because that's what we asked it to do here. And I probably didn't even need this stuff. I kind of put that in here. Output. So waste of code, right? Okay, Kristen, does that show you how to do a function?
Yeah, I think I know where I went wrong.
Okay.
Thanks.
Anybody else? Anything else on MATLAB or anything else about the exam? Michael, I'm glad you're here. I know you've said you've been fighting some illness. Maybe here.
Yeah, I'm here.
Good.
No, I've been feeling better recently. Yeah, it was just a week where I could barely move. Kind of
Yeah,
bad.
that's hard to get a week behind. So leverage with your teammates and classmates, shoot me an email, things we can all do to help you catch up.
All right. Thank you.
All right, that's all I have. Have a good week. It's nice to see your faces.
Thank you.
Thank you.
Thanks.
Thank you.
Have a good night.
You too.
Thank you. Hey, I actually did have two quick questions for you that
Okay.
weren't like super related to anything that anybody else had, and it was more of a specific to me thing.
Okay.
So So for one, I know that I'm probably gonna be starting the test at 3. Like you emailed me about earlier. Do I need to be like somewhere where like I can be like proctored or something like that,
No,
or?
on your own, and on your honor. I don't need to proctor you, and then we'll just start at 4 o'clock proctoring with everybody else. So I'll email it to you,
Okay.
just take it wherever you are.
Okay, that's fine. I just wanted to make sure, so I know what I was doing. Crap, there's a second question. I'm blanking on the second question that I had for you, but as soon as I remember it, I'll shoot you an email.
Okay, thank you,
Okay.
Zach.
All right, thank you.
Okay, bye-bye.
Bye.